In the heart of a black hole, where gravity crushes matter out of existence, two pillars of modern physics collide and shatter. General relativity, our theory of the cosmos on the grandest scales, predicts a singularity, a point of infinite density where all known laws break down. Quantum mechanics, our flawless guide to the subatomic realm, has a different, non-negotiable rule. Information can never be truly destroyed. This isn't just about data on a hard drive. It's the fundamental quantum state of every particle, a unique identifier containing its entire history. So, what happens when a star, with its quadrillions of particles and unique quantum information, collapses into a black hole? Classical physics says the information is lost forever, erased from the universe. Quantum mechanics screams that this is impossible. This is the black hole information paradox, a deep and violent contradiction that, for decades, threatened to unravel everything we thought we knew about reality. The resolution to this cosmic crisis didn't come from a grand unified theory, but from a deceptively simple observation about the black hole itself. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered something that defied all intuition. The total information content of a black hole, its entropy, was not proportional to its three-dimensional volume, as one would expect for any normal object. Instead, it was perfectly proportional to the two-dimensional surface area of its event horizon, the boundary of no return. This was a bombshell. Imagine a library. Intuitively, the number of books it can hold depends on the entire volume of the building, all the floors, all the shelves. But a black hole behaves as if all the books are somehow stored not inside the library, but as imprints on its outer walls. The Bekenstein-Hawking formula quantifies this with chilling precision. A black hole's entropy is equal to its event horizon area divided by 4 times the Planck area. The Planck area is the smallest possible unit of surface in the universe, a minuscule pixel of spacetime about 10 to the 70 square meters. This means you can count the maximum number of bits of information a black hole can hold by simply counting how many of these fundamental pixels fit onto its surface. The 3D interior becomes irrelevant. This insight was the first major clue that our understanding of space and information was profoundly wrong. It suggested that three-dimensional reality might be a kind of cosmic sleight of hand. The true information, the source code of reality, might be written on a lower dimensional surface. This is the seed of the holographic principle, a concept so radical it redefines the very fabric of existence. It proposes that our entire, seemingly voluminous universe, with its sprawling galaxies, intricate biology, and the very consciousness reading these words, could be a cosmic projection, a hologram. The idea was first formalized by Nobel laureate Gerard 't Hooft and later championed by Leonard Susskind, who realized its power to resolve the information paradox. If the information of an object falling into a black hole is smeared across and encoded on the event horizon, then it never truly crosses the boundary from a quantum perspective. It's stored on the surface, like data on a cosmic hard drive, ready to be slowly radiated back out as Hawking radiation. The paradox dissolves. But if this principle holds for a black hole, an object that represents the most extreme limit of physics, why wouldn't it hold for the universe itself? The cosmological horizon, the boundary of our observable universe, acts in many ways like a black hole's event horizon. Could it be that everything within our cosmic horizon, every particle, every field, every interaction across 13.8 billion years of cosmic history, is nothing more than a complex holographic image projected from information encoded on that distant two-dimensional boundary? This turns our perception of reality inside out. Space is no longer the fundamental stage on which the play of existence unfolds. Instead, space itself becomes an emergent property, a geometric illusion constructed from a more fundamental layer of quantum information living on a distant screen. The world isn't a container for information. The world is information, arranged in a way that creates the illusion of depth and locality. The implications are staggering, forcing us to question the nature of everything we perceive. If we are living in a hologram, is anything truly real? And if this isn't just a bizarre mathematical trick born from the edge of a black hole, where in the vast machinery of the cosmos can we find the proof? From that paradox, born in the abyss of a black hole, emerges a stunning mathematical dictionary for the cosmos itself. If our universe is a hologram, it requires a precise, rigorous framework to describe how a complex, three-dimensional world of gravity can be fully and equivalently described by a simpler, two-dimensional system of quantum particles without gravity. In 1997, theoretical physicist Juan Maldacena delivered just that. His groundbreaking paper introduced the ADS/CFT correspondence, a powerful conjecture that provided the first concrete mathematical model of the holographic principle. It stands today as the most successful realization of this mind-bending idea and a cornerstone of modern theoretical physics. The correspondence creates a duality, a perfect equivalence between two vastly different-looking theories. On one side, we have a theory of strings and quantum gravity existing in a specific type of curved five-dimensional spacetime called anti-de Sitter space, or ADS. Think of this as the bulk, the higher dimensional reality where gravity acts. On the other side, we have a conformal field theory, or CFT, which is a well-understood type of quantum field theory that lives on the four-dimensional boundary of that ADS space. This CFT has no gravity. It's a world of particles and forces more akin to the standard model of particle physics. Maldacena's conjecture states that these two descriptions are completely interchangeable. Every single entity, every process, every interaction in the complex gravitational world of the ADS bulk has a precise counterpart in the simpler, non-gravitational physics of the CFT boundary. This is the holographic dictionary. A black hole in the 5D bulk, for instance, corresponds to a hot thermal fluid of strongly interacting particles on the 4D boundary. The quantum entanglement of particles on the boundary corresponds to the geometric connection of spacetime itself, a wormhole in the bulk. This isn't just an analogy, it's a mathematically exact mapping. The power of this correspondence is that it connects a difficult problem in one domain to an easier one in the other. For decades, physicists struggled to understand the behavior of quark-gluon plasma, the superhot soup of fundamental particles that filled the early universe and is recreated in particle colliders like the LHC. The forces are so strong that traditional calculations fail. But using the ADS/CFT correspondence, physicists can translate this intractable problem into a much simpler one, calculating the properties of a black hole in a higher dimensional universe. The results from the black hole calculation can then be translated back, providing stunningly accurate predictions for the behavior of the quark-gluon plasma. This tool works. It has become an indispensable part of the theoretical physicist's toolkit, applied to problems in condensed matter physics, nuclear physics, and cosmology. It provides compelling circumstantial evidence that the holographic connection between gravity and non-gravitational systems is a deep feature of our universe. But is it a feature of our universe? While our cosmos is not an anti-de Sitter space, the success of the correspondence strongly suggests that the holographic principle is a correct and fundamental concept. This leads to the ultimate question: can we detect the holographic nature of reality directly? If our 3D world is a projection from a 2D surface composed of fundamental Planck-scale pixels, then our reality might not be smooth and continuous at the smallest scales. There might be an inherent graininess, a fundamental limit to the precision of information about an object's location. This could manifest as a tiny, inescapable jitter in the fabric of spacetime itself, a form of holographic noise. To hunt for this, scientists at Fermilab built the holometer, one of the most sensitive experiments ever conceived. Using a pair of powerful, co-located laser interferometers, they searched for a correlated jitter between the two devices, a signal that wouldn't be caused by local vibrations like seismic activity, but by a fundamental tremor in space-time itself. After years of running, the holometer's 2017 final results came back null. It found no evidence for the specific type of holographic noise it was designed to detect. However, this doesn't kill the holographic principle. It simply rules out the simplest models, suggesting that if our universe is a hologram, its projection mechanism is far more subtle and complex than we first imagined. The quest continues, pushing the boundaries of measurement to probe the very pixels of existence. What the holographic principle ultimately tells us is that the universe's most fundamental currency may not be matter or energy, but information. Reality, in its deepest sense, is not a collection of things, but a processing of bits. Every law of physics, every particle, and every force may simply be the emergent output of a vast quantum computation taking place on a distant cosmic boundary. Our three-dimensional experience is the stunningly complex, emergent user interface for a reality whose source code is written in a dimension we can never touch, but whose whispers we are finally beginning to hear.